low, and the gravity on these satellites is pretty low as well. Yeah, so it's not like in the mantle where the depth variations become important. Yeah. Okay. So walking further out on the plank, I'll talk about how convection may drive resurfacing. Okay, so I said before that there was this hope that if we coupled this viscous dissipation equation in with convection, that we would immediately be able to create chaos regions in our convection models and make pit spots and domes. Of course, that doesn't happen because these models are purely viscous. And our simple viscosity equation assumes that the viscosity essentially becomes infinite as the temperature gets lower. Okay, and so the convective plumes are always trapped underneath this essentially infinite viscosity upper layer. Okay, which of course is unphysical because the ice is very cold, okay, but it still is brittle and it will still fail. Okay, so one way of mimicking this behavior in a purely viscous convection model is to limit the viscosity of the upper surface with a prescription that looks like this. So you take the minimum of sort of two ways of estimating an effective viscosity. One of them is the temperature dependence, and the other is just taking simply and crudely a yield stress divided by the strain rate in that element. Okay, so when this type of prescription is used on sort of terrestrial planet problems, which are actually very similar to the icy satellite problems, this kind of rheology can generate a behavior that's vaguely plate tectonic-like. It's not perfect, but at least you get the stuff on the upper surface of the planet to deform in response to the underlying convection. Okay, so when this is used on Europa with a sufficiently low yield stress, you can actually create broad uplifts like what we're seeing here. This is a 45-kilometer wide simulation, and here Adam Shulman and Li Jihan have done this work, and they've limited the yield, or they've imposed a low yield stress for the upper surface ice, and they've gotten convective plumes to get up close to the surface and to make the kinds of uplifts and sort of spreading that you might expect to see on Europa. Okay, so that's all well and good, right? I mean, you run a model and it doesn't work, and so you get frustrated, so you change a parameter in the model to make it reproduce what you see, or make it reproduce what you think you see on an icy satellite. In my talk earlier in the week, I talked about how Enceladus is the satellite that will help us understand all other satellites. Okay, so this kind of simulation is great to do on Europa. Of course, there's not very many ways that you can really compare the results of this kind of simulation to the actual behavior of Europa, because we don't know the heat flux coming out of Europa's ice shell and how that varies from place to place. All we see are the remnants and the sort of scars of what convection has done to the surface in the past. But on Enceladus, by some amazing accident, we happen to be flying past it at the time of its activity. Okay, so here again, for the people who weren't here earlier in the week, is a plot of effective brightness temperature at the south polar terrain of Enceladus. The total heat flux coming out of this region, if you estimate it very carefully, is about 5.8 plus or minus 2 gigawatts coming out of this whole region here. Much of it obviously is concentrated in these narrow stripes. If you smear that heat flux out over the entire 70,000 square kilometer region of the ice shell, you get a surface heat flux of about 55 to 110 milliwatts per meter squared, which is pretty high. And everywhere else, high for an icy satellite, I should say.
It's like Earth.
It's like Earth, right. And everywhere else on the satellite appears to be completely geologically dead. I'll show you a picture in a couple of slides, and you can see the deadness. Here's the deadness. Okay, so this is the active region that's warm. This is the rest of the satellite. If you squint at this and you had a couple of beers and you're in Houston, Texas with Bill McKinnon, you could convince yourself that maybe there are remnant south polar terrains elsewhere on Enceladus. So maybe this process happened in other locations in the past, and this is just the latest incarnation that we're seeing today.
Is it just an accident to the south pole, or is that special?
It's thought that if you create this type of region with a hot, like a heat pulse, that creates a region of lower density. And it's thought that if you create that region of lower density elsewhere, on the satellite, that the satellite will actually roll over to put that region on the pole, either on the pole or on the equator, depending on.
And it doesn't have an influence that it's south and summer now in the Saturnian system. Or?
I'm sorry, you got to talk a little slower.
It's also south and summer on the Saturnian system now, or south
right,
and autumn. That doesn't really play a role.
I don't know. I mean, the equilibrium temperature, because it's southern summer at Saturn, the equilibrium temperature of the ice here is about 70 K, and at the North Pole, I think it's much colder. It's like 50. So whether the fact that you get, I hadn't thought about that actually, whether you get a warming of the surface ice and whether that may play a role in triggering this kind of process and starting, I don't know. That's an interesting idea. I hadn't thought about that. Okay. So, yeah, I mentioned that heat flux is big for an icy satellite, and it turns out that heat flux is actually larger than the upper limit on heat transport in stagnant wind convection in ice. That's just, that upper limit on heat transport is just based on the rheology of ice. Okay. So, if you can find a way to weaken the surface ice within the south polar terrain, you can actually get the convective plumes to kind of drag the surface along with it. Okay, this is a regime of convection called mobile mid-convection, which is similar, again, it's vaguely plate tectonic-like, and it arises when the yield stress of the near-surface material is low. This style of convection gives a heat flux that's comparable to that observed by the Sears instrument. The same conditions that give, the same sort of rheological parameters that give a convective heat flux comparable to that from Sears also predict that the surface in the south polar terrain should be in an extensional sort of regime, and that crustal extension would resurface this region in about 0.1 to 10 million years. That timescale turns out to be comparable to the sort of rough estimate of the surface age of the terrain, which is about 500,000 years. That crustal extension has to be balanced out by compression somewhere, and I suspect that is actually balanced by compression at the edges of the terrain. So you can see there's kind of folding at the cusps of these arcuate cracks that bound the south polar terrain. So you can imagine if this whole region is underlain by a giant convective upwelling and you're sort of pulling the surface apart, you could create compressional tectonics at the edges of the terrain if this adjacent ice was much stronger and this ice in here is weak. Okay, so oh, yeah.
Just to clarify, so the region, the cratered region up above, that's
this part.
How old is that?
This information is known. I don't have it at the top of my head, though.
I'm just wondering how often these true polar wander events take place.
Yeah. I don't know the age, but we can look it up. It was written up in an LPSC abstract this year. There's a student who's working on this. But you know, it's not like 0.5 million years and 1 million years.
Yeah.
It's like 0.5 million years and 1 billion years.
Yeah.
Yeah.
And so you could have these locations where this upwelling could be very long-lived.
Right. Yeah, I mean, it's not known how long such a system could be sort of self-sustaining like this. I mean, I think the possibility that this has happened before in the past is pretty interesting. I mean, the kind of, you know, if you think about it in a very broad sense, these tidally heated satellites may be wildly unstable, where the system has two solutions. There's a cold, non-dissipative solution for the interior temperature, and then there's a hot, highly dissipative solution. And, you know, a very tiny perturbation in the temperature or something, you know, maybe something else, or in the orbit, may be able to get you to kind of jump from one solution to the other. And so maybe the satellite has gone between hot and cold phases in the past.
There might be an intermediate solution, because you average that huge heat flux over the surface, and you get this heat flux.
Yeah.
But in fact, it is localized,
right.
And we know in our ocean that the most sensitive flux in terms of the influence on the thickness of the ice is the ocean heat flux.
Right.
So you can imagine if there is this annular ocean in Enceladus, that there's a local heat flux thins the ice cover, and that can drive an instability because it's thin here. It's gravitationally unstable as well as mechanically unstable. So that's somewhere between these.
Yeah. Yeah, I mean, you can imagine, you know, a perturbation in the heat flux of base of the ice shell from, for example, a silicate eruption at the surface of the rocky core. Is that the kind of thing you're thinking of? Yeah. Yeah.
I mean, just taking these numbers because you average them, and it's.
Oh. Yeah, let me clarify. I didn't average it over the whole satellite. I just averaged it over the region. Yeah. Yeah. But yeah. Yeah. Yeah.
So how does that heat flux, or the total heat flux in that region, compare to the total dissipation from tidal heating?
It doesn't match. It's too high.
It's too high.
It's too high. Yeah. So that suggests that this viscous dissipation model that I talked to you about is just like total BS. Yeah, and actually there's a graduate student at Brown who's doing experiments right now looking at attenuation and cyclically deformed ice, and she finds that the ice is about twice as dissipative at the frequencies for Europa and Enceladus as predicted by the Maxwell model. And I think that it's, you know, the rheology we're plugging into, you know, for ice that we're plugging into the Maxwell model, we're assuming it's diffusion creep and you know, making all these simplifying assumptions, and obviously that's not going on.
Well, she's at Brown, so she must talk to David Goldsby.
Yeah, she's working with Goldsby and Reed Cooper. So, yeah, they had some preliminary results they showed at a meeting in March in Houston, and I suspect they're going to have more results this year, and that viscous dissipation model that I showed you probably is going to go away and get replaced with something better, which is great. And again, what's fantastic about having such a capable spacecraft in Enceladus is now we actually have data that we can compare you know, to the models, and that's been driving a whole new set of lab experiments to try to bring, you know, the theory and the observation together. Yeah, I mean, if the Cassini spacecraft had blown up on the launch pad, none of this would have happened. So, yeah, it's really amazing that we've had this wonderful convergence.
So, the sort of length scale of those features is about 50 kilometers?
Yeah, they're about 5. I'm going to say this wrong, but I think we can look it up. I think they're about 50 kilometers or so apart, and they're something like about 500 kilometers long, something like that.
And guesses on the thickness of the ice again are?
Well, there's an absolute upper limit, which is 100 kilometers, and then you know, there have been various. I mean, I can just tell you the sort of proposed range. You know, if the shell is convecting, you know, it really can be whatever thickness it wants, but people tend to assume it's between 30 to 50 kilometers. That may be incorrect. Then there's a whole other camp of people that believe that the water that's erupting out of these lines is coming directly from an ocean, but only a local pocket of melt underneath the South Pole. And I don't really think that that's possible, because I think in order to get the tidal deflection that you need to create the heat in this region, you have to have a global ocean that mechanically decouples the ice shell from the interior. The local ocean camp thinks that the ice shell may be, you know, a kilometer or less than a kilometer thick. I mean, if you're serious about cracking all the way down to an ocean, you've got to have a really thin ice shell under here. But I don't know whether, you know, just given the thermodynamic properties of ice, I don't know whether that's, you know, you can push 55 milliwatts, you know, out of an ice shell. There's a finite F that you can push through this stuff before it melts. So, yeah. But I mean, it's really not well known. And unfortunately, we probably won't know for sure by the end of the mission. Okay. So I mentioned, hold on, I got lost here. So I mentioned that, that the possibility that the sort of combination of convection and a potentially weak surface on the South Pole of Enceladus can create this heat flux. I want to just give you an idea of what this style of convection might look like, but don't put too much stock in this, because this is from a grant proposal. So this is like the best looking graph out of all like thousands of graphs that I made. Okay, but basically you have the surface is held at about 70 K, the bottom of the ice shell is held at 273 K. There is some internal heating here, and I've assumed that the ice shell has a very low, very, very low yield stress, which I'll talk about in a second. And these are sort of surfaces of residual temperature. So this is the hot stuff is the yellow, and the cold stuff is this kind of pea soup green. Okay, and if you like squint at this, and you squint at the South Polar terrain, and you take my word for it, because this is from a grant proposal, you might be able to convince yourself that this is a plausible hypothesis for what's going on underneath the South Polar terrain. And of course, you know, the heat at the South Polar terrain is localized, right? And so what I am thinking about doing in the kind of next paper, the next iteration on this problem, is asking, well, what would happen if you just had these cracks be sort of passive weak zones in the ice shell? So if there's no active heating on these features, you know, what if they're just cracks and you have this huge heat flux coming up from underneath, and all the heat is just escaping through these narrow vents at the surface? Does that give you a heat flux comparable in magnitude and distribution to what has been seen by Sears? Okay, so I mentioned that in order to get this kind of convective-driven resurfacing that we've been looking for, and if you believe that there's a huge convective upwelling under the South Polar terrain, you have to have a weak surface. So how weak is weak? Okay, so the critical yield stress for the mobilization of that really cold upper surface material has been evaluated in the context of terrestrial planets. However, you know, we know all of the rheological parameters more or less for ice, and so we can evaluate this for an icy satellite as well. So Solomontov has done a whole bunch of simulations to characterize how this yield stress varies as a function of rheology. And he finds that in order for that lid material to move around and create that plate tectonic-like behavior, you have to have a yield stress less than this nasty equation, which depends on the thermal expansion of the material, the density, the gravity, the change in temperature between the top and bottom of the convecting layer. The gas constant is in there too with the rheology. The sort of characteristic temperature of the convecting interior, the activation energy, and this L sub H, which is a length scale over which plumes scrape horizontally against the upper lid and build up stresses in the upper lid. Okay, so if you plug the numbers in for an icy satellite with very low gravity and a relatively small temperature difference driving the convection, which is somewhat offset by the low activation energy for you know, ice creep, you come up with a yield stress which is frighteningly low. Okay, so it's about 10 to the minus 2 or 10 to the minus 3 MPa. So if you think in kilopascals, this is like 1 to 10 kilopascals, which is an embarrassingly small number. Okay, given that, you know, sort of general estimates of the yield stress from terrestrial ice sheets are much bigger, you know, a factor of 10 to 100 bigger than this critical value. And some of my own research points out that this is an unrealistic value for the yield stress of an icy satellite. I did some modeling with a student and Bob Papalardo, and we looked at the formation of these features called bands on Europa and how they might form in a style similar to mid-ocean ridges. You can estimate a yield stress associated with that kind of behavior, and we came up with a really high estimated yield stress. Okay, so one thing to take away from this graph is the fact that this yield stress is really low and maybe unphysically low. And another thing, if you want to take away from this graph, is the fact that, you know, if we can find a way to weaken the ice and make it essentially strengthless on the surfaces of these satellites, we might be able to drive the kind of resurfacing that we see in these somewhat weird convection models. Okay, so now I'm all the way out at the end of the plank, and I'm perched on the hairy edge of falling into the abyss. And this is all of the stuff that is kind of speculative and unpublished, and is what I've been thinking about recently. So I've been wondering whether the cyclical deformation of the satellite may actually affect the strength or the microstructure of the ice at the surface of the object. And when I say at the surface, I mean between a temperature, you know, all the way at the upper surface of 100 K down to sort of the brittle ductile transition, which is at maybe 210, 180 to 210 Kelvin. So these are really low temperatures, and at the very top, in the top few kilometers of the ice shell. Okay, so I think that there are a couple of different sort of weakening processes that I've been thinking about, and they may occur on several different length scales. Mostly I've been thinking about grain scale processes because I just finished a massive project to constrain the grain size inside an icy satellite, which focused on grain scale processes. So I learned all about that. Whether the stuff I learned is right or not, I don't know. But it was really fun, and so I thought I would take it 5 or 6 steps further and think about ways that you could weaken the ice at the grain scale. And then I also tried some weird and potentially blasphemous convection simulations to look at more sort of macro scale processes where, we have these equations that describe shear heating and viscous dissipation and surface weakening. So what happens if you throw all the equations into the model at once and hit return? And that's why I call this a blasphemous simulation, because you should obviously never do that. But I did it anyway just to see what would happen. And I'll show that at the end. So here are the sort of grain scale processes I've been thinking about, and these are like really poorly formed ideas. They're very nebulous because I don't even have the right scientific language myself to describe what I'm really thinking. So all I can do is draw pictures. Okay, so we know that, or we think we know, that deformation in water ice at these very low temperatures and these relatively high tidal strains could occur by grain boundary sliding and also possibly, possibly by grain boundary sliding, but certainly by dislocation creep. So what I started to think about was this kind of toy model. What if you had ice grains that were sliding back and forth in response to the cyclical daily tidal stress? And what if the grain doesn't really come back to where it started in the beginning? So you have 2 adjacent grains, they slide back and forth over that tidal time scale, and the ice shell is not going to be to within a grain boundary with where it was at the beginning of the cycle. So if you have a tiny bit of irreversible deformation in each tidal cycle in this near surface ice, maybe you start to introduce dislocations, and those dislocations can't really move around because the temperature is low in these regions. Okay, so walking out further on the precarious edge, this issue of the sort of huge viscosity at the top of your viscous convection model, and how that gives you behavior that is significantly unplate tectonic-like. This was a situation that was faced by the terrestrial mantle convection community about 10 or 15 years ago. And so now they think, and in general, sort of believe, that fractures in the crust of the Earth and the presence of water in the Earth's crust lowers the effective yield stress to the point where you can actually deform the surface of a terrestrial planet with the underlying mantle convection. Okay, and I've been thinking about whether introducing cracks in the region of the ice shell ranging from the surface down to the brittle ductile transition, whether at the micro or macro scale, may allow you to weaken the near surface ice. And one of the analogous processes that I've been thinking about is metal fatigue. So if you've never heard of metal fatigue, there's a great story that goes along with it. So they built one of the first passenger aircraft that was built was this thing called the Comet. And it was a really great plane, and it flew really fast, and it was really pretty looking. And about every Comet aircraft would work perfectly, and then about the 30th time that the thing would take off and fly over the Mediterranean, it would explode. They could never figure out what was going on. So finally, they decided to take one of these aircraft and simulate the stresses associated with pressurization and depressurization and with flight. And so they got these little pistons, and they bounced the wings up and down, and they pressurized and depressurized the plane. What they discovered was that the cyclical deformation on the wings of the plane made the wings fall off, and that tiny little cracks around the windows of the airplane introduced during that cyclical deformation of pressurization and depressurization, that created little cracks around the windows that caused the windows to pop out, and that's why the planes were exploding. And that was one of the ways that they first started to study metal fatigue. It's kind of a freaky story, but it's a very vivid it's a very vivid idea. You can envision in your mind that you know, you're cyclically deforming the satellite for like 100 million years. You know, what are you doing to the surface ice at that very low temperature? Okay, so this represents my extent of knowledge of microcracking in ice. It all fits on one slide and comes from a very small number of papers. But basically, there are a couple of methods that have been proposed for making microcracks in ice. And I should point out, though, that these methods are, you know, come from studying ice sheets on the Earth at much higher temperatures than we're talking about for Europa. And so there are these two methods. The first, you know, just related to concentrations of dislocations in the ice shell. I can't quite remember exactly how that works. And then there's a second method associated with grain boundary sliding. If you have a bumpy grain and you're shearing, you know, you're moving two grains across each other at the grain boundary, you can create local stress concentrations, and that can start to, you know, fracture the ice crystals. Both of these processes have sort of a critical stress that it takes to create a crack. And for the purposes of the grant proposal I wrote about this, I evaluated the critical nucleation stress for, you know, nominal ice parameters and a nominal grain size at the surface of 1 millimeter. And unfortunately, you know, these are pretty high stresses. They're certainly higher than the tidal stress. And I thought, well, what if the tidal stress and the convective stress are able to work together to make these processes happen? But, you know, that's, I mean, 1 megapascal for both processes seems like, you know, I don't really know if an icy satellite can generate that kind of stress in the ice shell. The other problem is that I mentioned that these processes work at sort of terrestrial ice sheet temperatures. And, you know, these critical nucleation stresses are temperature dependent because it takes a finite amount of time, and thus it takes a finite amount of time to create a crack. And so at a temperature of 110 Kelvin, appropriate for the surface of Europa, maybe at depth, it, you know, may not take that long, but at these very, very low temperatures, you know, there are no kinetics, so the time to nucleate a crack may be enormous at those low temperatures. Okay, I mentioned earlier that there was some relief in sight from lab experiments. The ice rheology people at Brown, which includes David Goldsby and Reed Cooper, are studying the effect of cyclical deformation on ice microstructure, and they're focused mostly on dissipation. The lab studies, of course, are crucial for understanding what happens in ice on these satellites and what happens to ice when it's forced at these frequencies. So I don't mean to undercut the importance of lab experiments here. It's really critical. But unfortunately, they're working with relatively small samples, and they're focused on grain scale effects. And I mentioned earlier that I suspect that whatever process is happening probably occurs at multiple scales. So at least from the lab experiments, we'll get information about the grain scale effects. But it would be nice to have a complementary understanding of what processes might be occurring just based on, you know, the principles of ice physics. And I've now exhausted my own personal knowledge. There's no one in my department and very few people at Colorado that think about this kind of thing. And so that's part of why I wanted to come to this meeting, was to talk to people here and see what I could learn.